What if the computer you're using right now wouldn't exist without ancient India? What if the numbers on your screen, the binary code running your apps, even the geometry that built Silicon Valley, all trace back to knowledge shared between two ancient civilizations separated by thousands of miles? What if I told you that while Greek philosophers like Pythagoras were discovering mathematical theorems, Indian mathematicians had already figured them out centuries earlier? And here's the twist. They might have actually met. They might have exchanged ideas in the bustling markets of the Persian Empire, in the royal courts where Greek physicians treated Persian kings, or along the ancient trade routes that connected the Mediterranean to the Indus Valley. Let's find out how this incredible exchange of knowledge happened and why it matters for every digital device you use today. The story begins not in Athens or Alexandria, but in the Indus Valley of ancient India, around 2,500 years before the Common Era. While we celebrate Greek geometry and mathematics as the foundation of Western science, there's a hidden chapter in this story that changes everything we thought we knew. The ancient Indians weren't just doing mathematics, they were inventing the very language that would one day power every computer, every smartphone, every digital device on this planet. But how did this knowledge travel? How did two civilizations on opposite sides of the ancient world end up sharing the same ideas? The answer lies in a network of connections that was far more sophisticated than most people realize. Trade routes, empires, diplomatic missions, and traveling scholars created a web of knowledge exchange that spanned from the Mediterranean to the Indian subcontinent. The risk here isn't just about getting history wrong, it's about understanding where our modern technology truly comes from. Every time you type on your keyboard, you're using a decimal system invented in India. Every time your computer processes information, it's using binary logic that an ancient Indian scholar named Pingala discovered while analyzing poetry, yes, poetry, in the 3rd century before the Common Era. Without understanding this exchange of knowledge between ancient India and Greece, we miss the entire foundation of computer science itself. We're taught that modern mathematics came from Greece, traveled through the Arab world and arrived in Europe. But what if the story actually starts in India? What if the Greeks were learning from the Indians just as much as we learned from the Greeks? What if the flow of knowledge was bidirectional, with ideas moving back and forth along the same routes that carried silk, spices, and precious stones? Here's where it gets interesting. Around 800 years before the Common Era, an Indian mathematician and priest named Bodhayana wrote down something remarkable in a text called the Shulba Sutras. The name translates to rules of the chord, and these were essentially technical manuals for Vedic priests who needed to construct fire altars with absolute geometric precision. The spiritual efficacy of their religious rituals depended on getting the shapes and measurements exactly right. In solving these practical problems, Bodhayana described a mathematical relationship. The area of the square on the diagonal of a rectangle equals the sum of the areas of the squares on its two sides. Sound familiar? We call it the Pythagorean theorem today, but Bodhayana wrote this at least 3 centuries before Pythagoras was even born. This wasn't just a lucky guess or a vague approximation. The Shulba Sutras give specific examples, listing what we now call Pythagorean triples, sets of 3 numbers that satisfy this relationship perfectly. The Shulba Sutras weren't just abstract mathematics either. These were practical instructions for building fire altars with precise geometric shapes. The ancient Indians needed exact measurements for their religious rituals, and in solving these problems they developed sophisticated geometry that wouldn't appear in Greece for hundreds of years. They needed to construct squares, circles, semicircles, trapezoids, and even complex shapes resembling falcons and tortoises. Each shape was intended to secure a different divine favor. A critical requirement was that different shaped altars, particularly for certain votive rites, must all possess the same surface area. This meant they had to develop methods for transforming one geometric figure into another while preserving its area. They had to square the circle, convert rectangles into squares of equal area, and perform other complex geometric transformations. This practical need drove the exploration of deep geometric properties and relationships, but here's what makes this connection even more fascinating. Ancient Greek and Roman sources actually tell us that Pythagoras traveled extensively. The historian Iamblichus, writing in the 3rd century of the Common Era, wrote that Pythagoras studied in Egypt for 22 years, was captured by the Persian army during their invasion of Egypt and taken to Babylon, where he studied for 12 years and may have even visited India before returning to establish his school in southern Italy around 530 before the Common Era. Now, most modern scholars are skeptical about the India trip specifically. There's no definitive proof that Pythagoras himself set foot in India. But think about this. During the Persian Empire, which lasted from around 546 before the Common Era, when they conquered the Greek cities of Ionia, to 330 before the Common Era, when Alexander the Great defeated them, both Greece and northwestern India were part of the same empire. This created unprecedented opportunities for cultural exchange. The Persian Empire was the first true superpower of the ancient world, stretching from Egypt and Greece in the west to the Indus Valley in the east. At its height under Darius I and Xerxes, it controlled approximately 8 million square kilometers of territory and ruled over nearly half the world's population at that time. This wasn't just a military conquest. The Persians built an extensive network of roads, the most famous being the Royal Road that stretched over 2,500 kilometers from Sardis in western Turkey to Susa in Persia. Along these roads traveled not just soldiers and tax collectors, but merchants, craftsmen, scholars, and diplomats from every corner of the empire. Greek merchants, doctors, craftsmen, and even sculptors worked at the Persian capital. Indian merchants and diplomats did too. They shared the same roads, the same trade routes, the same royal courts. This was a cosmopolitan world where ideas could flow freely across vast distances. We even have specific examples of this cultural mixing. Greek physicians worked at the Persian court for years. One named Democedes of Croton spent 2 years as the personal physician to King Darius I around 520 before the Common Era. According to the Greek historian Herodotus, Democedes was captured by the Persians, brought to the royal court, and became so valued for his medical skills that he was paid a talent of silver annually, an enormous sum. Another Greek physician named Ctesias of Kindus worked at the Persian court for 17 years from around 416 to 398 before the Common Era. He served as the personal physician to King Artaxerxes II and wrote extensive books about Persia and India based on conversations with Indian travelers and diplomats he met at the court. While his works are now lost, later Greek and Roman writers quoted from them extensively, preserving fragments of his observations about Indian culture, philosophy, and knowledge. And here's a detail that sends chills down your spine. In 517 before the Common Era, the Persian king Darius I commissioned a Greek navigator named Scylax of Carianda to sail down the Indus River and explore the possibility of sea trade between India and Persia. This wasn't just a military expedition, it was a scientific and commercial mission. Scylax actually wrote a book about his journey called the Periplus. It's lost now, but later Greek writers like Herodotus and Strabo quoted from it. He described Indian ascetics who lived outdoors and ate only wild grains. These were the yogis, the early practitioners of what would become Indian spiritual traditions. He described Indian cities, customs, and the flora and fauna of the region. This means that by the early 5th century before the Common Era, there was direct Greek observation and documentation of Indian culture. The knowledge was flowing, but the connections go even deeper. Archaeological evidence shows that trade between the Mediterranean world and India existed for millennia before the Persian Empire. By the late 3rd millennium before the Common Era, typical Mesopotamian cylinder seals have been found in the Indian city of Mohenjo-Daro, one of the major urban centers of the Indus Valley civilization, and carnelian beads from the Indus Valley have been found in Sumer in Mesopotamia. There was definitely trade going back and forth. The Sumerians even wrote about a place called Meluha, which scholars believe refers to the Indus Valley civilization. They mention Meluhan interpreters working in Mesopotamian cities and even Meluhan boats docked in Mesopotamian harbors. This suggests not just occasional contact but regular, sustained trade relationships. Where goods traveled, ideas traveled too. Then there's the Uluburun shipwreck from around 1300 before the Common Era. This was a ship with Greek sailors that sank off the coast of what's now Turkey. When archaeologists excavated it in the 1980s, they found goods from 7 different civilizations: logs from Nubia in Africa, blue glass from Mesopotamia, storage jars and a bronze statue from Canaan, scarabs from Egypt, including one with the name Nefertiti, swords and daggers from Italy and Greece, tin and lapis lazuli, probably from Afghanistan, which is right next to India. This ship was a floating marketplace of ancient globalization. It shows that by the late Bronze Age, there was already a complex network of trade connecting the Mediterranean, the Near East, and regions close to India. Ideas traveled along these same routes that goods did. A merchant who traded lapis lazuli from Afghanistan might also carry stories, mathematical techniques, or philosophical ideas from the regions he visited. The really interesting period for direct India-Greece contact is during the Persian Empire, from 546 before the Common Era, when Persia conquered the Greek cities on the coast of modern Turkey, to 330 before the Common Era, when Alexander the Great conquered Persia. Both Greece and India were connected within this massive empire. The Persian capital Persepolis was a cosmopolitan hub where Greek and Indian merchants, craftsmen, scholars, and diplomats regularly interacted. We have inscriptions from King Darius that mention Bactrian and Indian women from Gandhara who were in Persia. We read about Indian mercenaries serving in the Persian army. There was even an Indian colony near the city of Nippur in the 5th century before the Common Era. These weren't just isolated individuals. These were communities of people living and working far from their homelands, bringing their knowledge and culture with them. The Persian royal court actively imported Greek talent. Greek sculptors worked in Persepolis, and we can see their influence in the statues and reliefs which show typical Greek-style drapery and naturalistic human forms. We even know the name of one of these sculptors, Telephans of Phocea. According to Pliny the Elder, the Roman natural historian, Telephans was on par with the greatest Greek sculptors like Polycletus and Myron, but was little known in Greece because he spent his entire career in the workshops of the Persian kings Xerxes and Darius. If Greeks were traveling to Persia and Indians were traveling to Persia, they were meeting each other. They were exchanging ideas, and those ideas included mathematics and science. The Persian court was a melting pot of knowledge from across the known world. Now let's talk about something that will blow your mind. The thing you're using right now to watch or listen to this, your computer, your phone, it all runs on binary code, ones and zeros, on and off, true and false. This is the absolute foundation of all digital technology. Every app, every website, every digital photo, every song, every video, everything digital is ultimately just patterns of ones and zeros. We're taught that the German mathematician Gottfried Wilhelm Leibniz invented the binary system in 1689. He was fascinated by the Chinese I Ching and its system of broken and unbroken lines, and he formalized the mathematical properties of a base 2-number system. But here's what they don't tell you in computer science classes. 1700 years before Leibniz, an Indian scholar named Pingala was using binary logic. Not for mathematics initially, but for something completely unexpected, analyzing Sanskrit poetry. Pingala wrote a treatise called the Chanda Shastra, which means the science of meters, around the 3rd or 2nd century before the Common Era. This makes it one of the oldest works on prosody, the study of poetic meter and rhythm, in any language. Sanskrit poetry is based on patterns of long and short syllables, called guru and lagu. A guru syllable is heavy, taking 2 beats to pronounce, while a lagu syllable is light, taking 1 beat. The beauty and power of Sanskrit verse depended on the precise arrangement of these syllables into specific patterns called meters. Different meters were used for different purposes, some for epic narratives, some for religious hymns, some for love poetry. Pingala needed a way to systematically catalogue all possible combinations of these syllables in verses of different lengths. So he developed a method using exactly 2 symbols to represent them. This was the birth of binary representation. Think about what he was doing. He was taking complex poetic patterns and encoding them using just 2 basic units, long or short. Guru or lagu, 1 or 0. This is binary representation. He created a systematic way to count and enumerate combinations using what we would now recognize as binary numbers. His system even included the concept that later became Pascal's triangle, 1600 years before the French mathematician Blaise Pascal described it in 1654. But here's the truly remarkable part that connects to computer science. Pingala wasn't just using a binary-like system, he was doing algorithmic thinking. He created recursive formulas to generate all possible combinations. This is exactly what we do in computer science when we write algorithms. He was processing information systematically using a two-symbol system. Does that sound familiar? It should, because that's literally what every computer on Earth does. Let me give you a concrete example of how Pingala's system worked. Suppose you want to list all possible meters for a verse of 3 syllables. Each syllable can be either guru or lagu, so there are 2 to the power of 3, which equals 8 possible patterns. Pingala developed an algorithm to list them all systematically. If we represent guru as 1 and lagu as 0, the 8 patterns are 1 1 1 1 1 0 1 0 1 1 0 1 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0. This is exactly the binary counting from 0 to 7. Pingala then described a method to convert any given number into its unique binary representation of guru and lagu syllables. His algorithm is functionally equivalent to the modern method of repeated division by 2 and recording the remainders. This allowed him to not only list the patterns but also to organize them, effectively creating the first known description of a binary numeral system. It's important to note that Pingala did not use the symbols 0 and 1. His system was conceptual based on the properties of the two-syllable types. But the mathematical structure was identical to modern binary. It was later commentators on his work, such as the 10th century mathematician Halayuda, who explicitly used the symbol for 0, called shunya in Sanskrit, in their elaborations of Pingala's binary arithmetic. Halayuda's commentary on the Chanda Shastra explicitly describes a method for arranging binomial coefficients in a triangular formation, a structure he called Meru Prastara, meaning the staircase of Mount Meru. This is the same structure we now call Pascal's triangle in the West. This triangle provides a simple recursive method for computing binomial coefficients, which are essential in probability theory, algebra, and the analysis of algorithms. And it gets even better for understanding the foundations of computing. You need the concept of 0, not just as a placeholder but as an actual number you can calculate with. The Babylonians had a placeholder symbol for empty positions in their sexagesimal or base 60 number system, but they never treated 0 as a number in its own right. They used it to distinguish between numbers like 60 and 3600, but they didn't have rules for adding 0 or multiplying by 0. The ancient Indians did. The concept of 0 as a number developed gradually in India over several centuries. It appears in various forms in astronomical and mathematical texts, but the first formal mathematical definition of 0 and the creation of complete rules for arithmetic operations involving it came from an Indian mathematician named Brahmagupta around 628 of the Common Era. Brahmagupta was a brilliant mathematician and astronomer who lived in the city of Ujjain in central India. Ujjain was home to one of the world's foremost astronomical observatories and was a major center of learning. In 628, Brahmagupta completed his magnum opus, the Brahma-Sfuta Siddhanta, which means the correctly established doctrine of Brahma. This comprehensive Sanskrit text was primarily an astronomical treatise, but embedded within its 25 chapters were revolutionary mathematical concepts. Brahmagupta was the first mathematician in history to formalize 0 as a number in its own right, and crucially to establish a complete and systematic set of rules for operating with it. In Chapter 18 of the Brahma-Sfuta Siddhanta, he explicitly defines 0 as the result of subtracting a number from itself. He then proceeds to lay down the fundamental axioms of arithmetic involving 0. He stated that the sum of 0 and a positive number is the positive number, the sum of 0 and a negative number is the negative number, and 0 subtracted from 0 is 0. He also established the multiplicative property of zero. Any number multiplied by zero results in zero. These rules, presented in the poetic verse typical of Indian mathematical texts, were a monumental conceptual leap. They provided a logical and consistent framework for calculation, allowing zero to be integrated seamlessly into algebraic equations. Before Brahmagupta, mathematicians might use a symbol for an empty place, but they wouldn't think of adding 3 plus 0 or multiplying 5 by 0. Brahmagupta made zero a full citizen of the number system, with its own properties and behaviors. This was essential for the development of algebra, and ultimately, for the development of computer arithmetic. Simultaneously, Brahmagupta tackled the perplexing concept of negative numbers. While occasional fleeting references to negative quantities had appeared in other cultures, often as intermediate steps in calculations that were later discarded, Brahmagupta was the first to embrace them as legitimate mathematical entities. He created a powerful analogy, referring to positive numbers as dana, which means fortunes or assets, and negative numbers as rana, which means debts or liabilities. This practical framing, rooted in the world of commerce and accounting, allowed him to articulate the rules of signed arithmetic with stunning clarity. He stated that the sum of two fortunes is a fortune, the sum of two debts is a debt, the sum of a fortune and a debt is their difference, and if they are equal, the sum is zero. This makes intuitive sense. If you have $10 and owe $10, your net worth is zero. His rules for multiplication were equally groundbreaking and correct. The product of two fortunes is a fortune, positive times positive is positive. The product of two debts is a fortune, negative times negative is positive. This is the rule that often confuses students today, but Brahmagupta stated it clearly 1300 years ago, and the product of a fortune and a debt is a debt, positive times negative is negative. This was the first time in history that the complete and correct set of rules for operating with signed numbers was explicitly laid out. These rules are now hardwired into the arithmetic logic unit of every computer processor. When your computer adds a positive and a negative number, or multiplies two negative numbers, it is executing the logic first codified by Brahmagupta in the 7th century. However, Brahmagupta's exploration of the new arithmetic was not without its stumbles, particularly in the realm of division. While he correctly stated that 0 divided by any non-zero number is 0, his treatment of division by 0 was problematic. He asserted that a number positive or negative divided by 0 is a fraction with 0 in the denominator, a concept he left somewhat undefined. More significantly, he claimed that 0 divided by 0 is equal to 0. From a modern perspective, this is incorrect. Division by 0 is an undefined operation in standard arithmetic. Yet, this imperfection should not overshadow the magnitude of his achievement. Brahmagupta was venturing into entirely new mathematical territory. His attempt to define division by 0, while flawed, was a courageous effort to complete the logical system he had constructed. It was a problem that would continue to challenge mathematicians for centuries. It was another great Indian mathematician, Bhaskara II, who lived 5 centuries after Brahmagupta, who took a step forward on this problem. Bhaskara correctly stated that a non-zero number divided by 0 results in infinity, a concept he described as a quantity that is not altered by the addition or subtraction of any finite number. While still not a complete theory of limits, this was a significant conceptual advance, and even today, in modern computing, division by 0 is handled specially. When a program attempts to divide by 0, it triggers an exception or an error condition. In floating-point arithmetic, as defined by the IEEE 754 standard, division by 0 is handled by special values like infinity and negative infinity, while operations like 0 divided by 0 result in none, which stands for not a number. This shows that even today, handling this edge case requires special rules outside of normal arithmetic, highlighting the conceptual difficulty of the problem that Brahmagupta was the first to confront. Why does this matter for computer science? Because without 0, you can't have a proper decimal system. And without a decimal system, and the concept of 0, You can't develop the positional notation that makes binary mathematics possible. The Indian decimal system, with its use of zero and place value, is what allowed mathematical thinking to advance to the point where binary logic could be formalized. Every time a computer processes information, it's using concepts that trace directly back to these Indian innovations. The binary system from Pingala, the concept of zero from Brahmagupta and his predecessors, the decimal place value system that made positional notation possible. These aren't just historical curiosities. These are the fundamental building blocks of the digital age. Without them, modern computing simply would not exist. But we still haven't fully answered the crucial question. How did this knowledge travel between India and Greece? We know there was contact. We have archaeological evidence. We have historical accounts. But what were the specific mechanisms of knowledge transmission? One key mechanism was the translation of texts. When the Arabs conquered Persia and parts of India in the 7th and 8th centuries of the Common Era, they encountered a rich tradition of Indian mathematics and astronomy. They recognized its value and began translating Sanskrit texts into Arabic. One of the most important translations was done by a scholar named al-Fazari around 770 of the Common Era. He translated an Indian astronomical text called the Brahma Sfuta Siddhanta, the very work by Brahmagupta that formalized zero and negative numbers. This translation introduced the Indian numeral system, including zero, to the Islamic world. The impact was immediate and profound. Arab mathematicians quickly adopted the Indian numerals and began using them in their own work. One of the most famous Arab mathematicians, Muhammad ibn Musa al-Khwarizmi, wrote a book around 825 of the Common Era called On the Calculation with Hindu Numerals. This book explained the Indian decimal system and how to perform arithmetic operations using it. The book was later translated into Latin in the 12th century, and it was through this Latin translation that the Indian numeral system finally reached Europe. Interestingly, the word algorithm comes from the Latinized version of al-Khwarizmi's name, algorithmi. So every time we talk about computer algorithms, we're invoking the name of the Arab mathematician who helped transmit Indian mathematical knowledge to the West. But the transmission wasn't just one way, from India to the Arab world to Europe. There was also transmission from Greece and Mesopotamia to India. Modern historians who've studied Indian mathematics have found something remarkable. In the 6th century of the Common Era, a text called the Panka Siddhantika, written by the Indian astronomer Varahamihira, compiled 5 earlier astronomical and mathematical works. These were adaptations of even earlier works from Mesopotamia, Greece, Egypt, Rome, and India. That's right, Indian mathematicians were explicitly synthesizing knowledge from all these different civilizations. Another important text, the Surya Siddhanta from around 400 of the Common Era, contains the roots of modern trigonometry, but scholars have noted it contains many words of foreign origin, suggesting it was written under the influence of Mesopotamian and Greek mathematics. This shows that Indian mathematicians were not working in isolation. They were part of a broader network of knowledge exchange. Here's a statement that's going to be controversial, but it's based on serious academic research. Amartya Sen, the Nobel Prize-winning economist who's also a scholar of Indian mathematics, wrote, quote, "The golden age of Indian mathematics, which changed the face of mathematics in the world, was roughly from the 5th to the 12th century, and its beginning was directly inspired by what Indians were learning from work done in Babylon, Greece, and Rome." End quote. But he also emphasizes the reverse flow. He writes, quote, "Indian research was deeply influenced by the knowledge of foreign works on the subject, and in turn, Indian mathematics influenced mathematical work even in those countries, including Greece and Rome and Baghdad, from where Indians themselves had learned many things." End quote. This is the key insight. It wasn't one-way transmission, it was genuine exchange. The Indians learned from the Greeks. The Greeks may have learned from the Indians. Later, the Arabs learned from both. Then the Europeans learned from the Arabs and rediscovered Greek mathematics. This is how knowledge actually progresses, through networks of exchange, not through isolated genius. But here's what's fascinating from a computer science perspective. While the Greeks excelled at deductive geometry, proving theorems from axioms in the style of Euclid's Elements. The Indians excelled at algorithmic mathematics and systematic calculation. They developed methods for computation. They created systems like the decimal place value notation that made complex arithmetic possible. The Greek approach was theoretical and abstract, seeking to understand the eternal truths of mathematics. The Indian approach was often more practical and computational, seeking to develop efficient methods for solving problems. Both approaches are essential to modern mathematics and computer science. You need the theoretical rigor of Greek geometry to prove that your algorithms are correct, and you need the computational efficiency of Indian methods to actually implement those algorithms on real computers. Think about what Indian mathematicians gave us: the decimal system with positional notation, the concept of zero as a number, the binary representation in Pingala's work, early work on trigonometry, systematic methods for arithmetic calculations. These aren't just abstract mathematical concepts. These are the practical tools that make modern technology possible. Without the decimal system, we couldn't easily write software. Without zero, we couldn't develop algebra and calculus. Without the binary concept, we couldn't have invented digital computers. Without algorithmic thinking, we couldn't write computer programs. The Indian contribution was to systematize mathematics in ways that were computationally useful. They didn't just prove theorems, they developed procedures, algorithms, step-by-step methods for solving problems. This is the essence of computer programming. Now let's return to Pythagoras for a moment, because his story reveals something important about how knowledge spreads. The theorem we call Pythagorean was known to the Babylonians around 1900 to 1750, before the Common Era. They had clay tablets showing Pythagorean triples, sets of three numbers that satisfy the relationship a squared plus b squared equals c squared. The most famous tablet, called Plimpton 322, lists 15 Pythagorean triples. The theorem appears in the Indian Shulba Sutras around 800 before the Common Era, at least 2 centuries before Pythagoras. And Pythagoras himself, according to ancient sources, traveled widely in Egypt and Babylonia before founding his school in southern Italy around 530 before the Common Era. So did Pythagoras really discover this theorem, or did he learn it from other traditions and bring it to Greece? Modern scholars think he probably learned it from the Babylonians or Egyptians, or possibly through indirect transmission of ideas that originated in multiple places independently. The theorem is so fundamental that it's quite possible that different cultures discovered it independently. But the point is that Pythagoras was part of a network of knowledge transmission. He traveled, he learned from other cultures, he brought that knowledge back to Greece and taught it to his students. This is how knowledge spreads, not through isolated genius, but through travel, trade, and cultural exchange. Here's the thing though. In ancient times, knowledge was rarely attributed to individuals the way we do today. The Pythagoreans, the followers of Pythagoras, shared all their knowledge collectively and attributed everything to their master as a sign of respect. So even mathematical work done by his students generations later got credited to Pythagoras. Similarly, in India, mathematical knowledge was often embedded in religious or astronomical texts without clear attribution to individuals. The Shulba Sutras, for instance, are attributed to various ancient sages like Bodhayana, Apastamba, and Katyayana, but we don't know if these were real individuals or traditional names for schools of thought. What this means is that when we argue about who discovered what first, we're often missing the point. Ancient mathematics developed through collective effort, through transmission of ideas along trade routes, through students learning from teachers across cultural boundaries. The question isn't really who discovered the Pythagorean theorem first. The question is, how did this fundamental geometric truth become known across multiple ancient civilizations? And the answer is through the networks of exchange that connected the ancient world. Let me give you a perfect example of how this knowledge exchange worked in a way we can actually trace. The word sine in trigonometry has a fascinating etymology that reveals the path of mathematical knowledge. In Sanskrit, the term for sine was jaisha arda, meaning half chord, because sine was originally understood geometrically as half of a chord in a circle. If you draw a circle and inscribe an angle at the center, the sine of that angle is half the length of the chord that subtends the angle. Over time, the term jaisha arda got shortened to just jaisha. When Arab mathematicians encountered Indian mathematical texts in the 8th and 9th centuries, they transliterated jaisha into Arabic. But jaisha is a meaningless sound in Arabic. However, jeb, with the same consonants as how they transliterated it, is a good Arabic word meaning bay or cove. Since Arabic script doesn't specify vowels, later generations of Arab mathematicians used the term jib, thinking it was the actual word. Then in 1150, when the Italian mathematician Gerardo of Cremona translated Arabic mathematical texts into Latin, he translated jib, meaning bay, into the Latin word sinus, which also means bay or cove. And from Latin sinus we get the English word sine. In this one word, we see the interconnection of three mathematical traditions: Indian, Arabic, and European. The mathematical concept originated in India, was transmitted to the Arab world where it was integrated into Islamic mathematics, and then reached Europe where it became part of the Western mathematical tradition. And this happened over and over with different concepts. The decimal system traveled from India to the Arab world and then to Europe. The concept of zero followed the same path. Algorithmic methods for calculation, algebraic techniques, trigonometric functions, they all traveled along these interconnected routes of mathematical exchange. The Chinese mathematician Yi Xing, who lived between 683 and 727 of the Common Era, he traveled to India and brought back Sanskrit astronomical and mathematical works, which he translated into Chinese. The pioneering Arab mathematicians, including Al-Khwarizmi, from whose name we get the word algorithm, knew Sanskrit and studied Indian mathematics extensively. Al-Khwarizmi's book on algebra, written around 820 of the Common Era, uses the Indian numeral system throughout. European mathematicians like Leonardo Fibonacci in the 13th century learned the decimal system and zero from Arabic sources, who had learned it from Indian sources. Fibonacci's book Liber Abaci, written in 1202, introduced the Hindu-Arabic numeral system to Europe and showed how much more efficient it was than Roman numerals for calculation. It's an unbroken chain of knowledge transmission. And what made this transmission possible? Trade routes, empires that connected distant regions, merchants and scholars who traveled, diplomatic exchanges, and most importantly, the recognition that valuable knowledge could come from any culture. The ancient world was more interconnected than we often realize. The Silk Road wasn't just a route for trading silk, it was a route for trading ideas. The maritime trade routes that connected the Mediterranean to India weren't just for spices and precious stones, they were for knowledge. Every merchant ship that sailed from Alexandria to the ports of Western India carried not just goods but also ideas, techniques, and knowledge. Every caravan that traveled the Silk Road from China through Central Asia to the Mediterranean carried mathematical and scientific knowledge along with silk and spices. Now let's talk about what this means for computer science specifically. Modern computing didn't just appear out of nowhere in the 20th century, it built on thousands of years of mathematical development. The binary system that Gottfried Leibniz formalized in 1689 was inspired by his reading of the ancient Chinese I Ching, but the fundamental idea of binary representation goes back to Pingala in ancient India. The concept of zero, which is absolutely essential for computer arithmetic and for representing the off state in binary logic, came from Indian mathematicians like Brahmagupta. The decimal system, which we use to interface with computers, even though they work in binary internally, came from ancient India and was fully developed by mathematicians like Aryabhata in the 5th century. These aren't just historical footnotes, these are the foundational concepts that make computing possible, but it goes deeper than just these specific concepts. Indian mathematicians developed a way of thinking about mathematics that was fundamentally algorithmic. They wrote their mathematical knowledge in sutra form, concise verse-like rules that could be memorized and applied step by step to solve problems. This is algorithmic thinking. You have a procedure, you apply it systematically, you get a result. This is exactly how we write computer programs today. You create an algorithm, a step-by-step procedure, and the computer executes it. The Shilpa Sutras, for instance, give precise geometric constructions. Do this, then do this, then do this, and you'll get a file alter of the exact shape and size needed. That's an algorithm. It's a procedure that, if followed correctly, produces a specific result. This is the essence of programming. Pingala's work on binary combinations gave systematic methods for enumerating all possibilities. That's combinatorial algorithm design, which is a major field in computer science today. When you need to search through all possible solutions to a problem, you're doing combinatorial enumeration. When you need to count how many ways something can be arranged, you're using combinatorics. Indian mathematicians developed efficient methods for arithmetic calculation that minimized the steps needed. That's optimization, another core concept in computer science. They even worked on what we'd now call number theory and cryptography. Ancient Indian mathematicians like Aryabhata worked on solving linear congruences, which is fundamental to modern encryption systems. The RSA encryption algorithm, which secures most internet communications today, is based on number theory, specifically on the properties of prime numbers and modular arithmetic. Now, I'm not saying ancient Indians invented computers. That would be absurd. What I am saying is that the mathematical foundations that made computing possible were laid over thousands of years by many civilizations, and the Indian contribution to those foundations was absolutely essential and is often under-recognized. Let's look at some specific examples of how this plays out in modern technology. Every time you use the internet, you're relying on encryption to keep your data secure. When you see that little lock icon in your browser, it means your connection is encrypted using protocols like HTTPS. Modern encryption systems like RSA are based on number theory, specifically on the properties of prime numbers and modular arithmetic. Indian mathematicians were working on these kinds of problems over 1,000 years ago. Brahmagupta developed methods for solving what we now call Pell's equation, a type of Diophantine equation that's relevant to number theory. Bhaskara II, who lived in the 12th century, worked extensively on combinatorics and number theory. He developed the Chakravarla method, a powerful iterative algorithm for solving Pell's equation. This method was not rediscovered in Europe until the 17th century. These weren't just abstract mathematical games. They were developing systematic methods for solving complex computational problems. The same kinds of problems that underlie modern cryptography. Every search engine, every database, every system that needs to sort and organize information uses binary search trees and other data structures that rely on binary logic. This goes back to Pingala's systematic way of using binary representation to organize and enumerate combinations. The binary search algorithm, where you repeatedly divide a sorted list in half to find an element, is fundamentally based on thinking in powers of 2, which is binary thinking. Every programming language uses Boolean logic, true or false statements that control program flow. If this condition is true, do this. Otherwise, do that. This is binary logic. The concept that everything can be reduced to yes, no, true, false, 1-0 decisions is what makes programmable computers possible. And while George Boole formalized Boolean algebra in the 19th century, the fundamental concept of binary representation was already present in ancient Indian mathematical thinking. The artificial intelligence systems that are revolutionizing technology today rely on neural networks, which are ultimately just mathematical functions computed using linear algebra. And guess what? The efficient numerical methods for computing these functions depend on having a good number system with zero and positional notation. They depend on the ability to represent and manipulate large matrices of numbers efficiently. All of this traces back to the Indian innovations in number systems and calculation methods. I'm not trying to claim that ancient Indians predicted modern AI. That would be ridiculous. But I am pointing out that the mathematical infrastructure that makes AI possible was built over millennia, and Indian mathematicians made crucial contributions to that infrastructure. Let's talk about one more Indian mathematician who made extraordinary contributions, Aryabhatta. He lived from 476 to 550 of the Common Era during the golden age of the Gupta Empire. His only surviving work, the Aryabhatta, composed in 499, is a concise yet remarkably dense treatise written in just 118 Sanskrit verses. It stands as a landmark of the classical period of Indian mathematics, synthesizing and advancing knowledge in arithmetic, algebra, geometry, and most notably, trigonometry. Aryabhatta's contributions were twofold and interconnected. He played a crucial role in perfecting the decimal place value system, and he effectively invented the sine function as we know it, creating the world's first table of sine values. While the decimal place value system with zero had been developing in India for some time, Aryabhatta's work provided a clear and powerful articulation of its principles. In the Aryabhatta, he explicitly describes the hierarchical nature of the system with the phrase stanam stanam dasa gunam, which translates to place 10 times in value. This statement encapsulates the core concept of positional notation, where the value of a digit depends on its position, with each place representing a power of 10. So in the number 345, the 3 represents 3 hundreds, the 4 represents 4 tens, and the 5 represents 5 ones. This seems obvious to us now, but it was a revolutionary concept. Roman numerals, which were used in Europe at the time, didn't have this property. The symbol for 10, which is x, always means 10 no matter where it appears in a number. Aryabhatta developed a unique alphabetic cipher to represent numbers, using specific consonant-vowel combinations to encode large numbers in a compact, poetic form suitable for memorization. Using this sophisticated system, he developed algorithms for complex arithmetic operations, including methods for extracting square and cube roots that are remarkably similar to modern techniques. His mastery of the decimal system is perhaps best illustrated by his famous approximation of pi. He stated that the circumference of a circle with a diameter of 20,000 is approximately 62,832. This gives a value for pi of 62,832 divided by 20,000, which simplifies to 3.1416. This was the most accurate approximation of pi anywhere in the world at the time. The Greek mathematician Ptolemy, who lived in the 2nd century, had used a value of 3.14166, which is slightly more accurate, but Aryabhatta's value was still remarkably precise. Significantly, Aryabhatta described this value as asana, which means proximate or approximate, suggesting he understood that it was not exact and may have even intuited the irrational nature of pi, a concept not formally proven in the West until the 18th century. Aryabhatta's most revolutionary contribution, however, was in the field of trigonometry. While Greek astronomers like Hipparchus and Ptolemy had developed a form of trigonometry based on the chord of an angle in a circle, Aryabhatta took a different and ultimately more powerful approach. He focused on the relationship between half the chord and half the angle, a quantity he called Ardha Jaya, or simply Jaya. This Jaya is precisely the modern sine function, defined as the length of the side opposite the angle in a right-angled triangle inscribed in a circle of a given radius. He also defined the related functions Cauda, which is cosine, and Uttakrama Jaya, which is versine. This shift from the full chord to the half chord, which is sine, was a pivotal conceptual simplification that made trigonometric calculations far more elegant and efficient. Based on this new definition, Aryabhatta undertook the monumental task of creating the first ever table of sine values. He chose a large radius for his circle, 3,438 units, to achieve high precision. This value was derived from dividing the circumference of a circle, which is 360 degrees times 60 minutes per degree, which equals 21,600 minutes, by 2 pi. He then calculated the sine values for 24 angles in increments of 3.75 degrees from 3.75 degrees to 90 degrees. The Aryabhatta does not just present the final table, it provides the algorithm used to generate it. This method was a sophisticated application of finite differences. Aryabhata recognized a recursive relationship that the second-order difference of the signs is proportional to the sign value itself. This insight is a remarkable precursor to the differential equation y double prime equals negative y, which the sine function satisfies. Using this property, he could calculate each successive sine value based on the previous ones, a brilliant feat of numerical analysis. This sine table became an indispensable tool for astronomers in India and the Islamic world for centuries, allowing them to solve problems in spherical trigonometry and accurately predict the motions of planets and the timing of eclipses. The legacy of Aryabhata's work in modern computer science is immense. His refinement of the decimal system is of course foundational to all numerical computation. While computers operate in binary, they must constantly convert to and from the decimal system for human interaction, and the algorithms for these conversions rely on the same place value principles he articulated. His highly accurate value of pi is a classic benchmark in the history of computational mathematics, a field dedicated to finding ever more precise values for mathematical constants. More directly, Aryabhata's sine table is the ancestor of the lookup table, or LUT, a fundamental data structure in computer science. LUTs are used to store pre-computed values of a function to avoid expensive real-time calculations. In early computer graphics, video games and embedded systems with limited processing power, sine and cosine values were often stored in LUTs to speed up rotations and other geometric transformations. Even today, when you rotate an image on your phone or play a three-dimensional video game, the graphics processor is using trigonometric functions that are either computed using fast approximation methods or looked up in tables, just like Aryabhata did 1500 years ago. In digital signal processing, the fast Fourier transform or FFT algorithm, which is used to analyze frequencies in signals like audio and radio waves, relies heavily on the rapid calculation of sine and cosine values, often optimized using table-based methods. The numerical method Aryabhata used to generate his table, the method of finite differences, is a cornerstone of numerical analysis. It foreshadows more advanced techniques like Taylor series expansions and Runge-Kutta methods, which are used today to solve differential equations that model everything from planetary orbits and fluid dynamics to the behavior of electrical circuits and financial markets. Aryabhata's work demonstrates a profound understanding of how to approximate complex continuous functions with discrete computable values. This is the very essence of scientific computing. You can't compute an infinite number of values, so you compute a finite number and use them to approximate the function you need. By the 12th century of the Common Era, the rich mathematical tradition of India had reached a remarkable peak of sophistication. At the forefront of this intellectual flourishing was Bhaskara II, also known as Bhaskaracharya, which means Bhaskara the teacher. Born in 1114, he became the head of the same astronomical observatory at Ujjain that Brahmagupta had led 5 centuries earlier. Bhaskara II was a true polymath, and his principal work, the Siddhanta Shiromani, which means crown of treatises, completed in 1150, is a monumental encyclopedia of the mathematical sciences of his time. The work is divided into 4 parts: the Lilavati on arithmetic and geometry, the Bijaganata on algebra, the Graganata on the mathematics of planetary motion, and the Goladhyaya on spherical astronomy. Within these texts, Bhaskara not only refined and perfected the work of his predecessors but also made astonishingly original contributions to combinatorics, algebra, and most significantly, the foundational principles of calculus. In the Lilavati, a text charmingly named after his daughter, Bhaskara explored a wide range of arithmetic and geometric problems, including advanced topics in combinatorics. He provided clear rules for calculating permutations and combinations, essential tools for counting and probability. For example, he gave the formula for the number of permutations of n objects taken or at a time, and the number of combinations of n objects taken or at a time. These formulas are used constantly in computer science. When you need to know how many different ways you can arrange a set of items or how many different subsets you can choose from a larger set, you're using the formulas that Bhaskara clearly articulated. The Bijaganatha delved deeper into algebra, where he provided the first general solution to the so-called Pell's equation, which is m times x squared plus 1 equals y squared, a notoriously difficult type of indeterminate quadratic equation. To solve it, he developed the Chakravarla method, which means cyclic method, a powerful iterative algorithm that was not rediscovered in Europe until the 17th century. The Chakravarla method is a beautiful example of algorithmic thinking. It's a step-by-step procedure that, starting from an initial guess, iteratively improves the solution until it finds the exact answer. This is exactly how many modern algorithms work. You start with an approximation, you refine it, you check if it's good enough, and if not, you refine it again. This iterative approach is fundamental to numerical methods, optimization algorithms, and machine learning. His work on algebra also extended Brahmagupta's number system. While Brahmagupta had struggled with division by zero, Bhaskara took a step forward, correctly stating that a non-zero number divided by zero results in infinity, a concept he described as a quantity that is not altered by the addition or subtraction of any finite number. While still not a complete theory of limits, this was a significant conceptual advance. It is in his astronomical works, the Graganatud and Goladhyaya, that Bhaskara's most prescient discoveries are found. In order to accurately calculate the instantaneous motion of planets, he developed concepts that are the very essence of differential calculus. He understood that when a variable reaches its maximum or minimum value, its instantaneous rate of change, its differential, must be zero. This is the fundamental principle used in modern calculus for optimization problems. If you're trying to find the maximum profit, the minimum cost, the fastest route, or the best design, you use calculus to find where the derivative is zero. Bhaskara applied this idea to astronomy, for example, to calculate the precise moment when a planet's apparent motion is stationary. To do this, he considered infinitesimally small intervals of time and calculated the change in a planet's position over that interval. This led him to an expression for the derivative of the sine function. He showed that, for a very small change in an angle y, the change in sine of y is approximately proportional to cosine of y. This is equivalent to the modern formula, the derivative of sine y with respect to y equals cosine y. This was not an isolated trick. It was a method he applied to solve real astronomical problems, demonstrating a clear working knowledge of the principles of differentiation. Bhaskara's insights went even further, containing the seed of a crucial theorem in calculus now known as Rolle's theorem. Rolle's theorem states that if a differentiable function has equal values at two different points, then there must be at least one point between them where the derivative of the function is zero. In other words, where the function's slope is horizontal. In his analysis of planetary orbits, Bhaskara used an equation to describe the position of a planet. He noted that when the planet was at its closest point, called perigee, and its farthest point, called apogee, the value of a certain equation of motion was the same. He then reasoned that at some intermediate point in its orbit, the rate of change of this value must be zero. This is a perfect physical application of the principle of Rolle's theorem, a special case of the more general mean value theorem, which is a cornerstone of modern calculus. While Bhaskara did not generalize these results into an abstract formal theory of calculus as Newton and Leibniz later did, he discovered and applied its core operational concepts to solve complex physical problems, demonstrating a level of understanding that was centuries ahead of its time. The connections between Bhaskara II's work and modern computer science are deep and multifaceted. His advanced algorithmic solutions like the Chakravarla method exemplify the kind of sophisticated iterative problem-solving that lies at the heart of computer programming. Such algorithms are used in cryptography, optimization, and number theory. His work in combinatorics is directly relevant to the analysis of algorithms, database theory, and network design. where counting the number of possible states or configurations is often a critical task. The most profound connection, however, lies in his proto-calculus. The entire field of numerical methods, which is essential for scientific and engineering simulation on computers, is built on the principles of discretizing continuous functions. This is exactly what Bhaskara did when he considered infinitesimally small intervals of time. You can't compute a continuous function at every single point. There are infinitely many points. So you compute it at a finite number of points and use those values to approximate the function. This is numerical analysis, algorithms for optimization, which are central to fields like machine learning, for example, gradient descent, which finds the minimum of a function by following its derivative, artificial intelligence and operations research, are direct descendants of Bhaskara's insight that the derivative is zero at an extremum. Physics engines in video games and simulations that model the motion of objects do so by solving differential equations of motion step by step, a process that mirrors Bhaskara's method of calculating instantaneous velocity. When you play a video game and see realistic physics, objects falling, bouncing, colliding, the computer is solving differential equations in real time using numerical methods that are conceptually descended from the work of mathematicians like Bhaskara. Now you might be wondering, if Indian mathematics was so advanced and so important, why don't we learn about it in school? Why do Western textbooks focus almost exclusively on Greek and European mathematics? This is a complicated question with several answers. First, there's the legacy of colonialism. When European powers colonized much of Asia in the 18th and 19th centuries, they tended to dismiss non-European knowledge as primitive or inferior. This bias persisted in educational systems even after independence. Second, there's a language barrier. Ancient Indian mathematics was written in Sanskrit and related languages. It wasn't widely translated into European languages until the 19th century, and even then it wasn't well integrated into mathematics education. Third, there's a historiographical tradition. History of mathematics has traditionally been written from a European perspective. This narrative emphasizes the ancestors of European mathematics and downplays contributions from other traditions. But things are changing. Modern historians of mathematics are increasingly recognizing the importance of non-European mathematical traditions. Scholars like George Geverghese Joseph, who wrote The Crest of the Peacock, Non-European Roots of Mathematics, have documented the extensive contributions of Indian, Chinese, and other mathematical traditions. There's growing recognition that mathematics developed as a global enterprise, with different civilizations making crucial contributions. And there's increasing awareness that many concepts we attribute to European mathematicians were actually known much earlier in other cultures. The Pythagorean theorem in India, binary logic in Pingala's work, the decimal system and zero in ancient India, sophisticated algebra in medieval India. These weren't isolated curiosities. They were part of a rich mathematical tradition that deserves recognition. But here's what really matters for understanding our modern world. Computer science, the field that shapes our entire modern technological civilization, is built on foundations that are truly global. The binary system from Pingala, zero from Brahmagupta, the decimal system from Aryabhata, algorithmic thinking from ancient Indian mathematical methods, Greek geometry and deductive reasoning, Chinese contributions to algebra and computation, Arab advances in algebra and trigonometry, European development of calculus and formal logic. All of these pieces came together to make modern computing possible. No single civilization invented computer science. It emerged from the accumulated mathematical knowledge of human civilization, contributions from every part of the world over thousands of years. And this brings us back to where we started. The connection between ancient India and Greece. What the evidence shows is that these two great civilizations weren't isolated from each other. They were part of a broader network of exchange that included Mesopotamia, Persia, Egypt, and eventually China and the Arab world. Trade routes connected them. Empires like Persia brought them into direct contact. Scholars traveled between these regions. Ideas flowed along the same routes that goods did. Greek mathematicians learned from Babylonian and possibly Indian sources. Indian mathematicians later learned from Greek sources. Then both traditions influenced Islamic mathematics. Then Islamic mathematics influenced European mathematics. And eventually all these traditions came together in the development of modern mathematics and computer science. The story isn't Indians invented everything, or Greeks invented everything, or Europeans invented everything. The story is that human knowledge is cumulative and collaborative. Smart people in different places and times build on what came before, learn from other cultures, make new discoveries and pass them on. This is how progress happens. This is how we got from ancient mathematics to modern computers. And recognizing this doesn't diminish anyone's achievements. It actually makes the story more impressive. It shows the power of cultural exchange, of building on each other's knowledge, of learning from anyone who has something valuable to teach, regardless of where they're from. Think about what this means for today. We live in a more connected world than ever before. The internet lets us share knowledge instantly across the globe. Scientists collaborate internationally. Students can learn from teachers anywhere. We have the opportunity to create an even more vibrant, more productive exchange of knowledge than the ancient world had. But only if we're willing to recognize that valuable ideas can come from any culture, any tradition, any part of the world. Only if we're willing to give credit where credit is due and acknowledge the full history of how our knowledge developed. The next great breakthrough in computer science might come from anywhere. It might come from someone building on ancient Indian algorithms. It might come from someone applying insights from other mathematical traditions. It might come from someone synthesizing ideas from multiple cultures in a new way. That's how it's always worked. That's how it will continue to work. So let me bring this all together. Ancient India and Greece did share knowledge, probably both directly through the Persian Empire and indirectly through intermediaries like the Babylonians and Egyptians. Indian mathematicians developed crucial concepts including the binary system, zero, the decimal place value system, and algorithmic methods of calculation. These concepts are absolutely fundamental to modern computer science. They're not optional extras. They're the foundation. Greek mathematicians developed deductive geometry, formal proof systems, and theoretical frameworks that are also essential to modern mathematics and computer science. The combination of practical algorithmic thinking from India and theoretical deductive reasoning from Greece created the mathematical toolkit that made modern technology possible. And here's the most important point. When you use your computer, your phone, when you browse the internet, when you use any digital technology, you're benefiting from thousands of years of accumulated human knowledge. You're using the decimal system invented in ancient India. You're using binary logic that goes back to Pingala's work on Sanskrit prosody. You're using the concept of zero that Brahmagupta formalized. You're using Boolean algebra developed by George Boole. You're using transistors based on quantum mechanics. You're using programming languages based on formal logic. Every piece of technology you use is built on layer upon layer of human knowledge. Understanding this history isn't just about giving credit to people from the past, although that's important. It's about understanding how knowledge actually develops. It's about recognizing that the next breakthrough might come from anywhere, from anyone, from any tradition. It's about being open to learning from all sources of knowledge. And it's about appreciating the profound interconnectedness of human civilization. We're all part of the same story, the story of humans trying to understand the world, trying to solve problems, trying to build better tools, trying to share what we know with others. That story started thousands of years ago in places like the Indus Valley and ancient Greece. It continued through Persia, through the Arab world, through China, through medieval Europe, through the Industrial Revolution, through the Computer Revolution, and it continues today. So the next time someone tells you that computers are a purely Western invention, you can tell them about Pingala analyzing Sanskrit poetry with binary logic in ancient India. When someone says that modern mathematics started with the Greeks, you can tell them about Bardahina describing the Pythagorean theorem centuries before Pythagoras. When someone dismisses non-Western contributions to science and technology, you can tell them that the very numbers they're using to make that argument were invented in ancient India. And when you're working with any digital technology, take a moment to appreciate the thousands of years of human ingenuity that made it possible. Appreciate the Indian mathematicians who gave us zero and the decimal system. Appreciate the Greek mathematicians who gave us deductive geometry. Appreciate the Arab mathematicians who preserved and extended both traditions. Appreciate the Chinese mathematicians who developed their own rich tradition. Appreciate the European mathematicians who brought it all together into modern mathematics. Appreciate everyone who contributed to the cumulative knowledge that makes our modern world possible. Because at the end of the day, that's the real lesson here. Human knowledge isn't the property of any one culture or civilization. It's a shared heritage of all humanity. We all benefit from the discoveries made by people throughout history, regardless of where or when they lived. We all have the responsibility to add to that shared knowledge and pass it on to future generations. And we all have the opportunity to learn from each other, to build on each other's ideas, to create something greater than any one person or culture could create alone. That's what the exchange between ancient India and Greece represented. That's what the development of mathematics and computer science represents, and that's what we can continue to build together. The story of how Indian binary logic and Greek geometry came together to create modern computer science is a story about the power of cultural exchange. It's a story about how ideas transcend borders. It's a story about human ingenuity in all its forms. And it's a story that's still being written today, with each new discovery, each new innovation, each new connection between different fields and different traditions. So go ahead and explore this history more deeply. Read about Indian mathematics, read about Greek mathematics, read about how they influenced each other, read about all the other mathematical traditions around the world, and then think about how you can contribute to the next chapter of this incredible story. Because that's what it means to be part of human civilization. We inherit the knowledge of the past, we add our own contributions, and we pass it on to the future. That's how we got from zero to binary to the device you're using right now. And that's how we'll get to whatever comes next. Let me leave you with one final thought. The greatest ideas in human history weren't created in isolation. They emerged from exchange, from dialogue, from the meeting of different perspectives and different traditions. The mathematics that powers our computers came from India, Greece, Babylon, Arabia, China, and Europe, all contributing pieces to the puzzle. No single tradition had all the answers. But together, the cumulative knowledge of human civilization solved problems that no one culture could have solved alone. That's not a weakness. That's our greatest strength. That's what makes us human. We learn from each other, we build on each other's work, we create something bigger than ourselves. The ancient exchange between India and Greece was just one chapter in that ongoing story. Today we have the opportunity to continue that tradition of exchange on a global scale. We can learn from mathematical traditions around the world. We can combine insights from different fields. We can create new knowledge that will benefit future generations. But only if we're willing to look beyond our own cultural boundaries. Only if we're willing to give credit where credit is due. Only if we're willing to recognize that genius can emerge from anywhere. So yes, ancient India and Greece shared philosophical and scientific knowledge. Yes, Indian contributions to mathematics, especially concepts fundamental to computer science, were crucial. Yes, this history has been under-recognized in Western education. And yes, understanding this history matters for how we think about knowledge, innovation, and progress today. The computer you're using, the phone in your pocket, the internet connecting the world, they all exist because of thousands of years of mathematical development across many cultures. They exist because smart people in ancient India figured out binary logic and zero. They exist because smart people in ancient Greece figured out deductive geometry. They exist because smart people in medieval Arabia preserved and extended both traditions. They exist because smart people in modern Europe formalized these concepts into computer science. And they exist because all of these traditions were willing to learn from each other, to share knowledge, to build on each other's discoveries. That's the real story. That's the story that matters. That's the story we need to remember as we face the challenges and opportunities of the future. Ancient India and Greece didn't just share knowledge, they showed us how human progress actually works. Not through isolated genius, but through exchange, through collaboration, through the cumulative effort of humanity learning and building together. That was true 3,000 years ago, it's true today, and it will be true for as long as humans continue seeking knowledge. The zeros and ones running through your device right now are a testament to that truth. They're a reminder that we're all connected through the knowledge we share. They're evidence that the exchange between ancient civilizations wasn't just about the past, it shaped our present and will shape our future. So let's honor that heritage by continuing the tradition. Let's learn from all sources of knowledge. Let's share what we discover. Let's build something amazing together, because that's what humans do. That's what we've always done. And that's what will carry us forward into whatever comes next. Let me tell you about one more fascinating connection that shows just how intertwined these ancient civilizations were. When Alexander the Great conquered the Persian Empire in 330 before the Common Era, he didn't just bring Greek military power to the east, he brought Greek culture, philosophy and science. And more importantly, he created a new era of cultural fusion. After Alexander's death, his empire was divided among his generals. One of them, Seleucus Nicator, controlled a vast territory that included parts of India. Around 305 before the Common Era, Seleucus fought a war with the Indian Emperor Chandragupta Maurya. The war ended with a peace treaty and a marriage alliance. Seleucus gave Chandragupta his daughter in marriage and ceded large territories in what is now Afghanistan and Pakistan to the Mauryan Empire. In return, Chandragupta gave Seleucus 500 war elephants. But the most important part of this treaty wasn't the elephants or the territory, it was the exchange of ambassadors. Seleucus sent a Greek ambassador named Megasthenes to the Mauryan capital of Pataliputra, which is modern-day Patna. Megasthenes lived in India for several years and wrote a detailed account of Indian society, culture and knowledge called the Indica. The original text is lost, but it was extensively quoted by later Greek and Roman historians. Megasthenes described Indian cities, the caste system, Indian philosophy, and Indian scientific knowledge. He was particularly impressed by Indian astronomers and mathematicians. He wrote about their methods for measuring time, their astronomical observations, and their mathematical calculations. This was direct, sustained contact between Greek and Indian intellectual traditions. Megasthenes wasn't just observing from a distance. He was living in India, talking to Indian scholars, learning about their methods, and the exchange went both ways. Indian ambassadors were sent to the Greek kingdoms. Indian scholars traveled to Alexandria, which had become the intellectual capital of the Hellenistic world after Alexander's conquests. The famous Library of Alexandria, which aimed to collect all the knowledge in the world, almost certainly had Sanskrit texts. We know that the library had texts in many languages, and given the extensive trade and diplomatic contacts between the Hellenistic kingdoms and India, it would be surprising if they didn't have Indian mathematical and astronomical works. Unfortunately, the library was destroyed, so we can't know for certain what Indian texts it contained. But the circumstantial evidence strongly suggests that Greek scholars in Alexandria had access to Indian mathematical knowledge. This Hellenistic period, from Alexander's conquests in the late 4th century before the Common Era to the rise of Rome in the 1st century before the Common Era, was a golden age of cultural exchange. Greek kingdoms existed in Bactria, in what is now Afghanistan, right on the border with India. These kingdoms, known as the Indo-Greek kingdoms, were a unique fusion of Greek and Indian culture. Their coins show Greek gods on one side and Indian gods on the other. Their art shows Greek sculptural techniques applied to Indian religious subjects. This is where the famous Gandhara style of Buddhist art developed, showing Buddha with Greek-style drapery and realistic human proportions. If art and religion were being fused in this way, mathematics and science certainly were too. We have evidence of Greek astronomers working in India during this period. We have evidence of Indian astronomers using Greek astronomical models. The exchange was real, sustained and bidirectional. This wasn't just occasional contact. This was a period of genuine cultural fusion. Now let's talk about how this ancient knowledge exchange relates to a specific modern technology, GPS, the Global Positioning System. Every time you use GPS on your phone to navigate, you're relying on a chain of mathematical concepts that stretches back to ancient India and Greece. GPS works by using signals from satellites orbiting the Earth. Your phone receives signals from multiple satellites, measures the time it takes for each signal to arrive, and uses that information to calculate your position. This calculation requires several mathematical concepts. First, it requires trigonometry to calculate angles and distances on the surface of a sphere. This is spherical trigonometry, which was developed by Indian and Greek astronomers to track the motions of celestial bodies. Aryabhata's sine tables were created specifically for these kinds of calculations. Second, it requires the concept of zero and the decimal system to represent coordinates and perform calculations. Without zero, you couldn't represent latitude and longitude in the way we do. Third, it requires solving systems of equations. When your phone receives signals from 4 satellites, it has 4 equations with 4 unknowns: your latitude, longitude, altitude, and the exact time. Solving this system requires algebraic techniques that were developed over centuries, with significant contributions from Indian mathematicians like Brahmagupta and Bhaskara. Fourth, it requires understanding the geometry of space and time. GPS satellites are moving at high speeds and are far from Earth's surface, so their clocks run at a slightly different rate than clocks on Earth due to relativistic effects. Correcting for this requires Einstein's theory of relativity, which is built on differential calculus. And as we've seen, the foundational concepts of calculus were discovered by Bhaskara II in the 12th century, 500 years before Newton and Leibniz. So when you use GPS, you're using mathematics that has roots in ancient India and Greece. Or consider another technology, digital photography. When you take a photo with your phone, the camera sensor captures light and converts it into digital data. This data is then processed using algorithms to produce the final image. These algorithms use concepts from linear algebra, trigonometry, and calculus. The color of each pixel is represented using numbers in the decimal system. The image might be rotated or scaled, using geometric transformations that go back to the Shulba Sutra. If the image is compressed to save space, it might use the discrete cosine transform, which is related to Fourier analysis and relies on trigonometric functions. If the image is enhanced using filters, those filters are implemented using convolution, a mathematical operation that requires understanding of how functions behave, which is calculus. Every step of this process relies on mathematical concepts that were developed over thousands of years, with crucial contributions from ancient India. Or think about streaming video. When you watch a video on YouTube or Netflix, the video is compressed using algorithms like H.264 or H.265. These algorithms work by analyzing the video frame by frame, identifying patterns and redundancies, and encoding the information more efficiently. This requires sophisticated mathematical techniques, including discrete cosine transforms, which are based on trigonometry, quantization, which requires understanding of number systems and rounding, and entropy coding, which is based on information theory. Information theory, developed by Claude Shannon in the 1940s, is fundamentally based on the concept of binary information. Shannon showed that all information can be represented as sequences of bits, and he developed mathematical formulas for calculating how much information is in a message and how efficiently it can be compressed. This is a direct descendant of Pingala's work on binary representation, or consider machine learning and artificial intelligence. Modern AI systems like the large language models that power chatbots or the neural networks that recognize faces in photos are based on mathematical optimization. The computer is given a task like recognizing cats in images, and it learns by adjusting millions of parameters to minimize the error in its predictions. This optimization process uses gradient descent, an algorithm that calculates the derivative of an error function and moves in the direction that reduces the error most quickly. This is a direct application of the principle that Pingala II discovered, that at a minimum or maximum the derivative is zero. The algorithm is searching for the point where the derivative is zero by following the slope downhill. Every time an AI system learns something new, it's using calculus concepts that were first explored in 12th century India. The neural networks themselves are based on linear algebra. Each layer of a neural network performs a matrix multiplication followed by a nonlinear activation function. Training a neural network requires computing gradients of these matrix operations, which requires the chain rule from calculus. And all of these calculations are performed using floating point arithmetic, which is based on the decimal system and the concept of zero. So when you talk to a chatbot or when your phone recognizes your face, you're using technology that is built on mathematical foundations laid in ancient India. I want to emphasize again that I'm not claiming ancient Indians invented AI or GPS or digital photography. That would be absurd. These technologies required thousands of additional innovations and discoveries, but I am saying that these technologies would not be possible without the foundational mathematical concepts that were developed in ancient India and transmitted to the rest of the world. Let's also talk about the role of Indian mathematics in the development of algebra. The word algebra itself comes from the Arabic algebra, which appears in the title of a book by the Arab mathematician al-Khwarizmi. But the algebraic techniques in that book came largely from Indian sources. Indian mathematicians were solving algebraic equations centuries before al-Khwarizmi. Brahmagupta's Brahmasputa Siddhanta contains extensive sections on algebra, including methods for solving linear and quadratic equations. He gave formulas for solving quadratic equations that are essentially the same as the quadratic formula we learn in school today. He also worked on indeterminate equations, equations that have multiple solutions or require integer solutions. This is a branch of mathematics now called Diophantin analysis, named after the Greek mathematician Diophantus. But Indian mathematicians were working on these problems independently and developing their own sophisticated techniques. Bhaskara II's Bijaganita, which means the science of calculation, is a comprehensive treatise on algebra. It covers linear and quadratic equations, indeterminate equations, and even some cubic equations. The Chakravala method that Bhaskara developed for solving Pell's equation is considered one of the finest achievements of ancient mathematics. It's an iterative algorithm that always converges to the solution, and it does so efficiently. When European mathematicians finally tackled Pell's equation in the 17th century, they struggled with it. The English mathematician John Pell, after whom the equation is mistakenly named, didn't actually solve it. It was finally solved by the English mathematician William Brouncker in 1657, using a method that was essentially the same as Bhaskara's Chakravala method. Though Brouncker probably discovered it independently, the fact that it took European mathematicians 500 years to rediscover what Bhaskara had already done shows just how advanced Indian mathematics was. Indian mathematicians also made important contributions to the theory of series and sequences. Aryabhata gave formulas for the sum of the first in natural numbers, the sum of the first in squares, and the sum of the first in cubes. These are fundamental results in discrete mathematics. Madhava of Sangamagrama, who lived in the 14th century, discovered infinite series expansions for trigonometric functions like sine and cosine. He found that sine of x equals x minus x cubed, divided by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial, and so on. This is the Taylor series for sine, discovered 250 years before the Scottish mathematician James Gregory and 300 years before the English mathematician Brooke Taylor, after whom it's named. Madhava also discovered series for pi and for the arctangent function. These discoveries were part of the Kerala school of mathematics, a remarkable tradition that flourished in southern India from the 14th to the 16th centuries. The Kerala school made discoveries that anticipated many results of European calculus. They understood the concept of limits, they could differentiate and integrate trigonometric functions, and they used infinite series to compute values to high precision. Some historians have speculated that knowledge of the Kerala school's work might have reached Europe through Jesuit missionaries who were active in Kerala in the 16th century, possibly influencing the development of European calculus. While this is controversial and not definitively proven, it's certainly plausible given the extensive trade and missionary contacts between Kerala and Europe during this period. What's not controversial is that the Kerala school independently discovered many of the fundamental concepts of calculus. Whether or not this knowledge reached Europe, it demonstrates that Indian mathematicians were capable of the highest level of mathematical thinking. Now let's talk about the practical applications of Indian mathematics in ancient times. This wasn't just abstract theory. Indian mathematicians were solving real-world problems. Astronomy was a major driver of mathematical development. Indian astronomers needed to predict the positions of planets, the timing of eclipses, and the phases of the moon for religious and agricultural purposes. This required sophisticated mathematical models and computational techniques. The Surya Siddhanta, an ancient Indian astronomical text, contains detailed methods for calculating planetary positions. It uses trigonometry, algebra, and numerical methods. Indian astronomers understood that the Earth rotates on its axis, that the planets orbit the Sun in elliptical paths, and that eclipses are caused by the shadow of the Earth or Moon. These insights required both careful observation and mathematical modeling. Commerce was another driver. Indian merchants needed to calculate interest, exchange rates, and profit margins. This required arithmetic and algebra. The Lilavati, Bhaskara's treatise on arithmetic, contains many problems related to commerce. How much profit do you make if you buy goods at one price and sell them at another? How long does it take for an investment to double at a given interest rate? These are practical problems that merchants faced every day. Architecture and engineering also required mathematics. Building temples, palaces, and irrigation systems required geometric knowledge. The precise proportions of temple architecture, which were believed to have spiritual significance, required careful calculation. The construction of stepwells, which are elaborate multi-story structures for accessing groundwater, required understanding of geometry and structural engineering. Indian architects and engineers were using mathematical principles to create structures that still stand today, over 1,000 years later. Even music theory was connected to mathematics. Indian classical music is based on ragas, which are melodic frameworks defined by specific patterns of notes. The relationships between musical notes are based on mathematical ratios of frequencies. Indian music theorists understood these relationships and used them to create complex musical structures. This is similar to the Pythagorean understanding of music, where the Greek philosopher Pythagoras discovered that harmonious musical intervals correspond to simple numerical ratios. Whether there was direct influence between Indian and Greek music theory is unclear, but both traditions recognize the deep connection between mathematics and music. This connection continues today in digital audio processing, where sound is represented as numerical waveforms and manipulated using mathematical operations like Fourier transforms. Let me tell you about one more specific example that beautifully illustrates the connection between ancient Indian mathematics and modern computing: the concept of recursion. Recursion is a fundamental concept in computer science, where a function calls itself to solve a problem by breaking it down into smaller instances of the same problem. For example, to calculate the factorial of n, you can define it recursively. Factorial of n equals n times factorial of n minus 1, with the base case that factorial of 1 equals 1. This is a recursive definition because the function is defined in terms of itself. Recursion is used throughout computer science in algorithms for sorting, searching, tree traversal, and many other tasks. It's also the basis of recursive data structures like linked lists and trees. Now, here's the fascinating connection. Pingala's work on binary combinations and the enumeration of poetic meters used recursive thinking. To count the number of meters of length n, he recognized that you could add either a short syllable or a long syllable to all the meters of length n minus 1. This is a recursive relationship. Similarly, the Fibonacci sequence that appears in his work on Matromeru is defined recursively. Haleyuda's Meru Prastara, or Pascal's triangle, is generated recursively. Each entry is the sum of the two entries above it. This recursive thinking was fundamental to Indian mathematical methods. The Chakravarla method for solving Pell's equation is an iterative recursive algorithm. You start with an initial solution, apply a transformation to get a better solution, and repeat until you reach the final answer. This is exactly how recursive algorithms work in computer science. Indian mathematicians were also comfortable with the concept of infinity, which is related to recursion. In Hindu and Buddhist philosophy, infinity is a central concept. The universe is seen as infinite in space and time, going through endless cycles of creation and destruction. This philosophical comfort with infinity translated into mathematical comfort with infinite processes. Madhava's infinite series for sine and pi are examples of this. An infinite series is a sum that goes on forever, and understanding how such a series can converge to a finite value requires sophisticated mathematical thinking. This is related to recursion because you can think of an infinite series as a recursive process. To get the next term, you apply a rule to the previous term, and you repeat this infinitely. The concept of limits, which is fundamental to calculus, is about understanding what happens when you carry out a process infinitely many times. In modern computer science, we can't actually perform infinite recursion because computers have finite memory. But we use the concept of recursion to solve problems that would be very difficult to solve otherwise. And we use iterative approximations to compute values that would require infinite processes to compute exactly. For example, to compute the sine of an angle, a computer might use a truncated version of Madhava's infinite series, adding up the first 10 or 20 terms to get a good approximation. This is exactly the kind of thinking that Indian mathematicians were doing centuries ago. They understood that you could approximate complex functions using simpler operations repeated many times. This is the essence of numerical computation. Let's also consider the Indian contribution to the concept of algorithms themselves. The word algorithm, as I mentioned, comes from Al-Khwarizmi's name. But the concept of an algorithm, a step-by-step procedure for solving a problem, is much older. The Shulba Sutras are full of algorithms for geometric constructions. The Aryabhatiya contains algorithms for arithmetic operations and for generating sine tables. The Brahmasfuta Siddhanta contains algorithms for solving equations. Indian mathematical texts were written in sutra form, which is a very concise, almost code-like style. A sutra is a short verse that encodes a rule or procedure. To understand it, you need to unpack it and apply it step by step. This is very similar to how we write computer code. A line of code is a concise instruction that the computer unpacks and executes. The sutra style of mathematical writing encouraged algorithmic thinking. Moreover, Indian mathematicians were concerned with efficiency. They wanted to find the fastest, most efficient methods for calculation. This is a central concern in computer science. When we design an algorithm, we don't just want it to work, we want it to work efficiently. We analyze the time complexity and space complexity of algorithms to understand how they scale as the input size grows. Indian mathematicians were doing similar analysis, though not in the formal way we do today. They would compare different methods for solving the same problem and choose the one that required fewer steps. Aryabhata's method for generating sine tables using finite differences is more efficient than computing each sine value independently. Bhaskara's Chakravarla method is more efficient than brute force search for solutions to Pell's equation. This focus on efficiency is a hallmark of good algorithmic thinking. I also want to talk about the role of Indian mathematics in the development of the scientific method itself. The scientific method, as we understand it today, involves making observations, forming hypotheses, testing those hypotheses through experiments or calculations, and refining the hypotheses based on the results. Indian mathematicians and astronomers were doing this. They made careful astronomical observations, developed mathematical models to explain those observations, used their models to make predictions, and then checked whether the predictions matched reality. When they didn't, they refined their models. This iterative process of observation, modeling, prediction, and refinement is the essence of the scientific method. Aryabhata's astronomical models were based on careful observations. When later astronomers found discrepancies between his predictions and their observations, they developed improved models. This is how science progresses. The Indian tradition also emphasized the importance of proof and verification. While Indian mathematical proofs were often different in style from Greek proofs, they were rigorous. Indian mathematicians would provide examples to illustrate their methods. They would check their results using alternative methods, and they would provide logical arguments for why their methods worked. Bhaskara's works contain many examples of this. He would state a rule, give several examples of its application, and then provide a logical justification for why the rule is correct. This emphasis on verification is crucial in computer science. When we write a program, we don't just assume it works. We test it with various inputs, we check edge cases, and we try to prove that it's correct. The Indian mathematical tradition's emphasis on verification and proof is part of the foundation of this approach. Now let's address a question you might be thinking. If Indian mathematics was so advanced, why didn't India develop computers first? Why did the computer revolution happen in the West in the 20th century? This is a complex question with many factors. First, the development of computers required not just mathematical knowledge, but also advances in engineering, electronics, and materials science. The invention of the transistor, which is the basic building block of modern computers, required understanding of quantum mechanics and semiconductor physics. This knowledge developed primarily in Europe and America in the early 20th century. Second, the computer revolution was driven by specific needs, particularly military needs during World War II. The first electronic computers were built to calculate artillery trajectories and to break enemy codes. This concentrated effort and funding accelerated development. Third, by the time computers were being developed, India was under British colonial rule. Colonial policies had disrupted traditional education systems and had oriented the Indian economy towards serving British interests rather than developing indigenous technology. The intellectual and economic resources that might have been used for technological innovation were constrained by colonialism. Fourth, the development of computers required a specific historical trajectory. It required the formalization of logic by George Boole, the development of the concept of a universal computing machine by Alan Turing, the invention of electronic components, and the convergence of all these ideas in the mid-20th century. This happened to occur in the West, but it built on mathematical foundations that were global, including crucial contributions from India. It's also worth noting that India has become a major player in the computer industry today. Indian engineers and computer scientists have made enormous contributions to software development, artificial intelligence, and information technology. Many of the world's leading tech companies have large research and development centers in India. Indian programmers have contributed to open-source projects that power much of the internet. In a sense, India is reclaiming its place in the story of computation. The mathematical heritage that Indian scholars developed over thousands of years is now being applied to cutting-edge technology. This is the continuation of the story we've been telling. Knowledge flows across cultures and across time. The ancient Indian mathematicians who developed binary logic, zero and algorithmic thinking couldn't have imagined computers, but their ideas made computers possible. And today's Indian computer scientists are building on that heritage. Let me also address another important point. Some people might worry that emphasizing Indian contributions to mathematics somehow diminishes European contributions. This is absolutely not the case. European mathematicians made enormous contributions that were essential to the development of modern science and technology. The formalization of calculus by Newton and Leibniz, the development of non-Euclidean geometry, the creation of set theory and mathematical logic, the invention of the computer by Turing and von Neumann, these were all crucial achievements. The point is not to replace one narrative with another, but to recognize that the true narrative is more complex and more interesting. It's a story of global exchange and collaboration. European mathematics built on foundations that included Indian, Greek, Arab, and Chinese contributions. and in turn, European mathematical ideas spread around the world and influenced other traditions. The history of mathematics is not a competition between civilizations, it's a collaborative human endeavor. Every culture that has contributed to this endeavor deserves recognition, and understanding the full history makes us better mathematicians and scientists. When we recognize that valuable ideas can come from any culture, we become more open to learning from diverse sources. When we understand that progress comes from exchange and collaboration, we become better collaborators. When we see that the greatest achievements build on the work of many people across many cultures and many centuries, we become more humble and more appreciative of the collective nature of human knowledge. This is the real lesson of the story of Indian mathematics and its connection to computer science. So what can we take away from all of this? First, the mathematical foundations of computer science are truly global. They include contributions from ancient India, Greece, Babylon, China, the Arab world, and modern Europe. No single culture can claim to have invented computer science. It emerged from the accumulated knowledge of human civilization. Second, the specific contributions from ancient India, including binary representation, zero, the decimal system, and algorithmic thinking, were absolutely essential. Without these concepts, modern computing would not be possible. Third, knowledge spreads through networks of exchange. Trade routes, empires, traveling scholars, and diplomatic missions all played a role in transmitting mathematical knowledge across cultures. Fourth, the exchange was bidirectional. Indians learned from Greeks and Babylonians. Greeks and Arabs learned from Indians. Everyone learned from everyone. This is how knowledge actually progresses. Fifth, recognizing this history doesn't diminish anyone's achievements. It enriches our understanding and shows the power of cultural exchange. Sixth, this history is relevant today. We live in a globalized world where knowledge flows freely across borders. The next great breakthrough could come from anywhere. We need to be open to learning from all cultures and all traditions. Seventh, the story isn't over. The mathematical and computational traditions that began thousands of years ago continue today. Every time someone writes a new algorithm, proves a new theorem, or builds a new technology, they're adding to this ongoing story. And finally, we all have a role to play. Whether you're a student, a teacher, a programmer, a scientist, or just someone who uses technology, you're part of this story. You can learn about the history of the ideas you use. You can appreciate the contributions of people from all cultures. You can share knowledge with others, and you can add your own contributions to the collective knowledge of humanity. The story of ancient Indian mathematics and its connection to modern computer science is ultimately a story about human potential. It shows that humans in any time and any place, given the right circumstances, are capable of profound insights and remarkable achievements. The Vedic priests who needed to build perfect altars developed sophisticated geometry. The Sanskrit poets who wanted to catalogue meters discovered binary logic. The astronomers who wanted to predict eclipses invented trigonometry. The merchants who needed to calculate interest formalized algebra. Each of these groups was solving practical problems, and in doing so they discovered universal truths that transcend their original context. This is the power of mathematics. It's a language for describing patterns and relationships that exist in the world. And once discovered, these patterns can be applied in contexts that the original discoverers never imagined. Pingala, analyzing Sanskrit poetry in the 3rd century before the Common Era, could never have imagined that his binary system would one day power devices that could store all the world's knowledge and communicate instantly across the globe. Brahmagupta, formalizing the rules of zero in the 7th century, could never have imagined that zero would become the foundation of digital logic. Aryabhata, creating sine tables for astronomical calculations in the 5th century, could never have imagined that those tables would be used to render 3-dimensional graphics in video games. Bhaskara, discovering the principles of calculus in the 12th century, could never have imagined that calculus would be used to train artificial intelligence systems. But their discoveries, made for their own purposes in their own time, turned out to have universal applicability. This is the beauty of mathematics. It's not just useful for the problems of today, it's useful for problems we haven't even thought of yet. And this should give us hope for the future. The mathematical and scientific work we do today might have applications we can't even imagine. The problems we solve today might provide the tools for solving problems 1,000 years from now. This is why it's so important to pursue knowledge for its own sake, not just for immediate practical applications. You never know when a seemingly abstract idea will turn out to be exactly what's needed to solve a crucial problem. The ancient Indian mathematicians who developed these concepts weren't trying to invent computers, they were trying to understand the world, to solve the problems they faced, and to push the boundaries of human knowledge. But in doing so, they created the foundations for technologies that would transform human civilization thousands of years later. So as we use our computers, our smartphones, our GPS devices, our digital cameras, all the technology that surrounds us, let's remember the long chain of human ingenuity that made it all possible. Let's remember Baudhayana, measuring chords to build perfect altars. Let's remember Pingala, analyzing the rhythms of Sanskrit poetry. Let's remember Brahmagupta, wrestling with the concept of nothing and making it into something. Let's remember Aryabhata, calculating the motions of the heavens. Let's remember Bhaskara, discovering the mathematics of change. Let's remember all the Greek mathematicians, the Babylonian astronomers, the Arab scholars, the Chinese inventors, the European scientists, everyone who contributed to the collective knowledge that powers our modern world. And let's commit ourselves to continuing this tradition. Let's learn, let's discover, let's share, and let's build. Because that's what humans do. That's what we've always done, and that's what will carry us forward into the future.